Thank you for showing up. We will get right underway. The first talk of the day is, or first talk of the afternoon is Stanislav Zivny.
Thank you, Eric. Thanks for all coming. I'd like to start by thanking the organizers for inviting me. It's great to be here, this wonderful meeting. So in this talk, I want to present a joint work with Johan Tappe from Paris. And informally, the result says the following. For a large class of interesting computational problems, two things can happen. It's sort of an algorithmic dichotomy result. Either a very simple algorithm, a linear program relaxation, solves every instance in this class, or, the other case, a very powerful SDP relaxation doesn't solve this class of problems. So how do we formalize large class of interesting computational problems? Well, this is what Libor did for us. So the framework of constraint satisfaction problems, and I hope you all went to the talk in the morning, is allows you to talk about lots of problems rather than individual problems. And when I say CSPs here, constraint satisfaction problems, I mean most of the decision problems. You should think of problems like 2-SAT, 3-SAT, 3-lane equations with 3 or 3 coloring. And there's an impressive body of literature on decision CSPs. A lot of great people, some of them are here, and a lot of breakthroughs in recent years. And in an almost disjoint universe with some overlap, but a very small one, there's possibly even bigger body of literature, larger body of literature of work on max CSPs when you try to maximize the number of satisfied constraints, perhaps approximately, and you should think of problems such as max cut, max 3-lane, max 3-SAT, and so on. And again, there's been huge progress in this area in the last 2 years. Lots of breakthroughs. I'll mention some. In this talk, I want to talk about a more general class of CSPs, which includes these two special cases. So it allows you to mix both the sort of decision CSPs, homomorphism problems if you like, and max CSPs, purely optimization problem. It allows you to talk about things like vertex cover, which is not a decision CSP if you talk about non-uniform CSPs with a fixed template. It allows you to include things like locally defined submodular functions and other stuff. So let me give you 3 examples of problems you all know in this framework. Especially the first one will look strange. So this is a 3 coloring. And the way I want to see it is, even though it's a decision problem, I want to see it as an optimization problem, sort of. It's a minimization problem where I minimize over all possible assignments of the 3 available colors to the vertices of the graph. And the objective function is given as the sum of binary terms. And each term comes from an edge in the graph. And the function sitting there is in fact the relation, but I want to see it as a function which returns 0 or infinity in the obvious thing. So if the 2 arguments are the same, it's infinity 0 otherwise. So minimizing this function really asks about, is it possible to get a proper coloring? Is the smallest value for this expression 0, or is it infinity? This is a purely decision problem. The second example is max cut in disguise in the minimization version, minimum uncut, where you try to minimize the number of edges in red, so within the 2 partitions. And in this talk, I want to see this problem as a minimization problem where you minimize over assigning 0 and 1s to the vertices of the graph. So 0 and 1 correspond to the 2 partitions of the graph. And the objective function you minimize is, again, sum of binary terms. And each term comes from an edge. And this time, the function looks like this. If the 2 arguments are the same, it returns 1. If they are different, it returns 0. Again, for every assignment, it corresponds to partition, gives you the size of the complement of the cut. And you try to minimize this. And the third and final example is the vertex cover problem. And here, I'll view it as, again, minimization problem. You minimize over assignments of 0 and 1s to the vertices of the graph, 1 meaning in the cut, 0 meaning out of the cut. And the objective function looks slightly more complicated this time. So the first sum comes with unary terms for each vertex in the graph. And essentially, it counts the number of vertices assigned 1. So it's the size of the cover. And the second sum makes sure that the vertices be selected by assigning the 1 is indeed a cut. So the function makes sure that, so this function psi comes from the edges of the graph, and it's not possible to assign both endpoint zeros. It would correspond to an edge that is not covered. Okay, so these are 3 examples, purely decision, purely optimization, and sort of mix of the 2. Mixing both sort of just rational values and these infinities, these forbidden values. So these are just 3 examples of this general framework, which is called valued or general valued CSPs. Is a generalization of CSP and max CSP or min CSP to be precise. And the definition is as follows. So useful and common notation is to denote by Q bar the set of rationals extended with positive infinity. And a VCSP or valued CSP instance is given by n variables, x1 through xn, a finite domain, D, and an objective function, I of x1 through xn. And the objective function is given as the sum of terms. Each term is a fixed RD function, so it's given explicitly by all possible assignments. So if the RD is k, it's mod of d to the k values. And the goal is to find an assignment of labels from d to the variables that minimizes I exactly. So it's an exact optimization problem. Now if you vary the codomain of the functions, the phis, you get, as I said before, CSP as a special case, min or max CSP. It doesn't matter because we do things exactly. It was approximately, this wouldn't be true. But we'll consider the case when it's Q bar, so the most general version. And one more piece of notation. So VCSP of gamma is the class of all VCSP instances of this form, where all the phis in the objective function come from a fixed set of functions gamma. So gamma is called the constraint language or template. This is the most studied class of CSP and VCSPs when you fix the set of allowed constraints or functions in your instance.
You just fix it by listing them or describing certain language?
So in this talk, we'll assume that gamma is finite on a fixed finite domain D, so it can be given explicitly. Sometimes people consider infinite gammas as well. Okay. So the main result, now you know at least two things. By the large class of interesting computational problems, I mean these general valued CSPs parameterized by a language. And by solving it, I mean minimizing these, the objective function exactly. And what do I mean by a simple linear program relaxation? So every VCSP instance has a very natural linear program relaxation, which is called a basic or canonical LP relaxation. And sometimes it works, and sometimes it doesn't, meaning it has fractional solutions. And there's a systematic way of making the relaxation stronger and stronger. There's this hierarchy of Shelley-Adams, which has a parameter, L, and the bigger L, the better. If L equals to n, then actually the relaxation is tight. So let me tell you the definition. So this is the VCSP instance. We make sure that every subset of at most L variables, where L is the parameter of the Shelley-Adams relaxation, appears in the scope of some function, some phi. If it doesn't, we can always throw it in and put there some, say, constant zero function. It doesn't change the objective function at all. Now, the variables of the relaxation are lambdas with two parameters. I gives you the number of the term in the objective function, so from 1 to q. And sigma is an assignment of labels to the variables in the ith term in the objective function. And it's a variable which is between 0 and 1, and you should think of it as a probability. Probability that the ith term in the objective function, the variables in the ith term get assigned values according to sigma, sort of local assignments. And now the relaxation says the following. So the constraints are all lambdas should be non-negative. Well, if we want them to be probabilities. For the local assignment sigmas, which return infinity, we want those lambdas to be 0. We don't allow these infinite values. So that's what it means here. It's not in the domain of the phi. If you look at the ith term in the objective function and you sum the probabilities over all possible assignments to the ith term, they should sum up to 1, as probabilities should. And the most interesting part is the last set of constraints. So this is a marginalization. If I look at two terms, say the ith one and jth one, and the set of variables of the jth one is a subset of the set of variables of the ith one, I want a marginalization. So the probability that, say, the jth term gets assigned tau is equal to the probabilities of the assignments, is the sum of the probabilities of the assignments that extend tau to the bigger scope I. And here's the parameter L. So this is done only if the smaller scope is of size at most L. Now, if these variables were 0, 1 valued, rather than between 0 and 1, the objective function of the LP relaxation would be the same as of the VCSP instance. But because it's not, it can be generally between 0 and 1. It's not quite the same, and you should think of this as the expectation, the expected value of the objective function with respect to this probability distributions, these lambdas. Now, if L is fixed, this is a polynomial size relaxation, you can solve it. So the simple LP relaxation in this result corresponds to the third level of the shell Adams. Now, what do I mean, the powerful SDP relaxation? So this is a Lasserre relaxation. So Lasserre relaxation of semi-definite programs is a strengthening of the shell Adams hierarchy, where you replace the lambdas, which previously were just numbers between 0 and 1, by vectors from some finite dimensional vector space, say from R to the T. And you also have one more extra variable, which lambda sub 0. So they are now in bold because they should be vectors. And the relaxation isn't, I mean, there are a lot of equivalent ways of doing it, but this is the one from the literature, so it doesn't correspond precisely to the previous one. You could make them almost syntactically identical. So let's have a look. So we want this lambda 0 to be unit vector. You should think of these lambdas so that if you take the norm of it squared as the probability, so this quantity you should think of, what is the probability that the ith term gets assigned values according to sigma, as before. So for instance, if the local assignment gets an infinite value, then it's 0. If you take in a product of any two, it's non-negative. This one should be unit vector. If you look at any two assignments, an assignment to the ith term, sigma sub I, an assignment to the jth term, sigma sub j, if they have some variables in common and they assign different values, they are sort of inconsistent, so you want this inner product to be 0. And this corresponds to the marginalization in a way. So this says that if you take 4 scopes, ij, rs, and if the union of the variables in the ith and jth scope is the same as the union of the variables in the rth and s scope, and if you take assignments to these scopes, which are consistent, meaning on the variables that have in common get assigned the same values, then the inner product on the left-hand side should be equal to the inner product on the right-hand side. And the last set of constraints says that if you look at scopes of size 1, so scopes of size 1 sort of correspond to variables on the original VCSP instance. And if you look at all the possible assignments, which in this case, I didn't denote them by sigma, but by A and D, because it's just a single label. So the sum of the sort of probabilities is equal to 1. So this is a very strong relaxation. Again, if L is fixed, this is a polynomial size relaxation which can be solved up to a small additive error, up to an arbitrary additive error, exactly. And if the L is equal to n, the number of variables, similar to the Shell-Adams hierarchy, you actually have a tight polytope. So it precisely corresponds to the convex combinations of the solutions to the original instance. The trouble is that then the relaxation is not of polynomial size, so it's not clear how to solve it, right? Even if you want to say, look at the dual, it's still not quite clear.
So what is intuition behind lambda?
So the intuition behind these lambdas. So the intuition is that rather than using Shell-Adams where you have just probabilities, these times you have vectors. So the squares of the norms are still, you think of them as probabilities, but now they don't come from arbitrary numbers, but they have to come from inner products of vectors. So it means you restrict the types of probabilities you get. Not sure whether it helps or not.
Something like amplitudes.
Pardon?
Like amplitudes in quantum mechanics.
Oh, I don't know anything about quantum, but maybe you can tell me something about quantum after the talk.
Because
The real value. The real.
yes, that's a difference.
If they were complex,
That's why.
it would look
Although they are not complex, no. Sorry, did I say complex in a way?
They would look a lot like quantum.
Right. So that was confusing with the real.
No, they come from R to the T, from some fixed T.
Right.
Okay?
Well, the thing is, with the complex, you can't really then say it's positive semi-definite. Right?
Yes.
Okay, more questions? Clarifications? Okay. So the second part of the theorem says that even if you look at, so if the level of Lasserre you look at is n, that solves the problem exactly, but there is some constant such that say C times nth level of the Lasserre hierarchy doesn't solve the problems.
Can you tell us what makes a relaxation stronger than another? I mean, you call it a strong relaxation. Here you say a powerful relaxation.
All right. Okay. So these say the kth level of the Lasserre hierarchy is known to be tighter than the kth level of the Shell-Adams hierarchy, meaning as the polytope is tighter. So it's a fewer fractional solutions. Okay. So this hierarchy of Lasserre actually now in the last 2 years people realize that it's the same as the sum of squares algorithm. So this is the most popular name these days. So it has nice connections to proof complexity. Sum of squares. Albert knows a lot about these, but unfortunately he's not around. Okay. So for instance, in the area of approximation, these relaxations are the basis of the most powerful algorithms people use, right? The Comans-Williamson breakthrough from the 90s for MaxCut was the algorithm was pretty much the first level of the Lasserre hierarchy. And then Aurora and others had this approximation algorithm for sparse cut. So that was the third level of the Lasserre hierarchy, pretty much. So, okay.
And there is also some connection between Sarali-Adams and the number of variables in some logic. Isn't that the Maneva and...
Yeah, there is some. And I think Anuj knows a lot about these things. So maybe he can answer the question later. Yeah? Okay. So I want to make this this theorem precise. And in order to do it, I'll need polymorphisms. But you know everything about polymorphisms now because of Libor's talk. So you know that polymorphisms are closure operations on feasible solutions, pretty much. That's the intuition. So formally, Libor talk about relations. This is a function. But if you have a function, you look at the set of feasible tuples. I mean those that don't return infinite values. So in the case of relations, it would be just the tuples in the relation. And if you take any, if it's an M array operation is a polymorphism of phi, if you take any M feasible sort of solutions, or tuples that are in the domain of phi, and you apply F component-wise, you get another feasible solution. So the examples to have in mind is projections, sometimes called dictators, which are trivial polymorphisms of all functions, because they return one of the arguments. And Libor mentioned in the morning an example of max, binary max operation, which explains why Horns are destructible. Here's a different example. Majority is a ternary operation on 0, 1, which explains why 2-sat is tractable. So really, the reason why 2-sat is solved in polynomial time is because actually it admits majority as a polymorphism in the algebraic point of view. So these are polymorphisms. Polymorphisms capture decision CSPs. If you want to talk about channel valued CSPs, which include CSP as a special case, but also include other problems, you need to generalize it, and you go to fractional or weighted polymorphisms. And these are probability distributions on polymorphisms with some desirable properties. So here's the definition. I have a function again phi. I look at, say, on the set of M array polymorphisms of phi, and a probability distribution on this set is a fractional polymorphism if it satisfies this inequality for all possible x1 through xm's. So you should think of these x1 through xm as sort of feasible solutions to phi. You look at the average value of these m, so that's the right-hand side. And on the left-hand side is the expected value with respect to the probability distribution that is the fractional polymorphism. How do I call it there? Omega. So I'll give you one example which probably most of you know. It's a very important example. This is the example of submodular functions. So you could define submodular functions. I mean, the usual definition has intersections and unions and so on. But if you know submodular functions, then actually you can define the class of submodular functions as the set of functions that admit this particular probability distribution as a fractional polymorphism. So the probability distribution on the set of binary operations that gives probability half to min and half to max, and 0 to everything else. Yes?
So that naively, it looks like maybe you could take a probability distribution over dom phi instead of just taking exactly m.
Probability distribution over dom phi.
Right, and then add them up on the right-hand side of the inequality. Could you do that? Or,
Well, no, because here you take just m of them, right?
yeah.
This could be more than m, right? Or what do you mean?
Yeah, I mean, just take some distribution over the elements of dom phi, and then can you generalize this somehow? Or-
Well, I mean,
oh, they
but-
have to be. I see. M is the arity of. Okay, we can talk about this.
More questions? I mean, unfortunately, this is slightly technical, but if you know submodular functions, hopefully this example helps. If you don't submodular functions, then, well, you should think of them as probability distributions over polymorphisms. Not arbitrary probability distributions, but some that have some satisfy some linear inequalities. Okay. Now, a bounded width condition, which you've heard about actually in the morning. So if you have a set of operations C on domain D, then we say that this set satisfies the bounded width condition BWC if for every m at least 3, there's m-ary operation in this set that satisfies this weak and U property. So if all the arguments but one are the same, then the answer stays the same. This is an example of an identity. Well, for the people who know these things, examples of C's that satisfy the bounded width condition is if you take, say, the binary operation min we saw before, max, and you generate the clone, functional clone from min. If you take majority and you generate the functional clone from this operation. Okay, so this is the bounded width condition. And now I can finally make it the statement more precise, even if you didn't get the definition. So another piece of notation. The support of gamma is the set of operations that get positive probability in some fractional polymorphism of gamma. So in the case of submodular functions, min and max would be in the support, but others as well, other operations as well. So now what does the theorem say? It says that if gamma is an arbitrary finite set of functions on some fixed finite set D, then either the support of gamma satisfies the bounded width condition, in which case any instance of VCSP over gamma can be solved exactly by the third level of the Shell-Adams hierarchy, or the support of gamma doesn't satisfy the BVC, in which case this class contains problems that cannot be solved even by linearly many levels of the Lasserre SDP relaxation. An algorithmic dichotomy theorem. And actually, by a breakthrough result of these guys, Lee, Raghavendra, and Steuer, this was a best paper award at Stock last year, the second one actually implies that no polynomial size semi-definite program relaxation of this class of problems can solve it exactly. So, which is astounding. I mean, this result. Okay. So, where does this condition come from? So, in a very important series of papers, and we have some of the authors here, it was established that this condition precisely captures the power of local consistency methods for decision CSPs. So this is known as the bounded width theorem due to Barta and Kozhik and independently obtained by Andrei Bulatov. And later on, actually, Libor and Martin used the techniques from that result to show that this condition also captures all max CSPs that can be robustly approximated. So these guys, Victor Delmon and Ray Crokin, got the sort of the hardest part, if you like, and they did the algorithmic part. So now, with this result I just mentioned, you can see how natural and robust this condition is. It not only captures these two, it also captures the solvability of general valued CSPs by SDP relaxations of polymer size. So I'll just say a few words about how you would want to prove such a thing. So for the tractability part, I mean, the things I like about this part of the result is a very simple algorithm. When it was announced, this is from last year, actually only this first part, it covered known cases that were known to be tractable, but via much more complicated algorithms. And there were some new cases, such as the majority in the support, which surprisingly wasn't known to be tractable before. And the proof heavily relies on the bounded width theorem. It's a key ingredient. So what we do, we show that if the third level of the LP relaxation has a solution, then actually you can find a solution that is closed under all the operations that are in the support. And once you have that, you can go to decision CSPs, use bounded width theorem, and then use LP duality to go back and show that actually the relaxation is tight. In the second part of the theorem, actually in this case, something much stronger is known. in the approximation community. So if you have a language gamma which corresponds to equations, linear equations, then you not only know that the linear level of the Lasserre doesn't solve them, but doesn't even approximate them well. And these are great results. So it was done for the Boolean, in the Boolean case by Schoenberg in 2008. It was actually a rediscovery of an old result from the proof complexity by Grigoriev. Then Tulsiani did it for equations over an abelian group of prime power. And finally Chan, who was a student here actually in Berkeley, did it for all abelian groups. So this is the starting point. So someone's done this for us. And then again, we use the boundary width theorem, which gives us that if a supportive gamma doesn't satisfy the boundary width condition, you can get your hands on equations. So the work is to show that getting to the equations doesn't change the non-solvability of the Lasserre linear relaxation. So there are these algebraic constructions Libor talked about in the morning, like going to the core, PP interpretations, PP definitions, expressibility. That's what you do. And all these reductions were known to preserve computational complexity. So what we do, we show that they preserve non-solvability of the Lasserre hierarchy. So this is my last slide, I believe. So I would like to compare it with some known results in the approximation community. So on the one hand, we get a weaker result in the approximation guys because we only deal with exact solvability. On the other hand, we get a stronger result. In particular, this is a characterization when convex relaxations work exactly. And furthermore, we do it in the framework of general valued CSPs, which is as general as you can get. So in the approximation community, people know lots of stuff about inapproximability of max CSPs. So they 0-1 valued functions. And then they can often say things about other problems, like say Vertex cover, by problem-specific reductions. So they take max CSP as a starting point, and they do a reduction to some concrete problems. They have no tools how to actually prove it for, say, all general valued CSPs, where you can mix, they call it strict constraints, like in the Vertex cover, you want to say, both endpoints have to be taken. I think that's it. Yeah, okay. I'm done. Thank you for your attention.
Are there any more questions?
Maybe you said that in the first few minutes that I wasn't here, sorry. How does this relate with soft CSPs?
And what do you mean by soft CSPs?
So soft CSP is, you have constraints which are interpreted as functions from assignments to variables to a C-semi-ring, to a semi-ring.
So this is the semi-ring where you have the semi-ring is Q-bar, so it's the rationals together with positive infinity.
So probably soft CSPs might be a bit more general, probably.
Much more general, but I don't think the other semi-rings are that interesting. But yeah.
There are a few.
There are some which might be interesting, but maybe not from the optimization point of view. Yeah. So this is for one particular concrete semi-ring, the min plus.
Yeah, okay.
Okay.
Thanks.
Does it answer your question? Yeah.
Yeah.
Thank you. More questions?
Libor, I think I just hand up to somebody else.
Yeah, there was no. Okay.
So can you go to the previous slide? You said Schoenberg for ZP, then for powers, and then for abelian groups. Is it necessary? You don't have any kind of reduction to cores, to homomorphic equivalence factor, something? Because then this would make it not so.
Yeah. I think it could be done, but it's easy just to take their result and yeah. Fair point. Yes.
Any other questions? Thank you.